Now, we start a new topic called Polya Theory. Let us start with one of the questions that we have visited many times so far in this course. That is, suppose I give you this 5 squares in a row, and I give you n different colors, and I ask you to color these squares using your choice of colors. Right? So you can choose for each cell, you can decide which color that you want to use, and then you have to color. Now, the first question that rises in combinatorics is how many different ways I can do this coloring, right? So how many different ways are there to color these 5 squares given n colors? Of course, the answer is very easy, right? For every square, we know that there are n choices for the colors, right? And I can, I am free to choose whichever color that I want. So I have n choices for each of the 5 boxes. So n raised to 5 colorings in total, right? So I get n raised to 5 distinct colorings of these squares. Now we can add some restrictions. For example, I say that, okay, we allow rotation of this figure by 180 degrees, right? I can just, rotate the entire thing by 180 degree. And then I say that if I can get one coloring, right, a fixed coloring of this strip by rotating another coloring, right? Then I will say, I consider them to be equivalent, right? I don't distinguish between them. So if under rotation I say that, okay, the coloring that is given to this, right, is the same, then I can say that the colorings are equivalent, right? For example, a coloring like this, if I rotate, I will get the same coloring, right? Now, then we can ask like how many different colorings are there now, right? How many inequivalent colorings are there? So one can think of trying to solve this. We see that, okay, if I have n raised to 5 colorings in total, if I reflect them, I will get a set of colorings, and these colorings are equivalent, right, for corresponding, right? Like if I take any coloring, its reflection is also equivalent. So maybe I can try to divide by 2, but then there is a problem. If I divide all the colorings by 2, will it work? Well, the problem is that like some colorings might be counted twice for this thing, right? For example, I might have a coloring where the reflection also gives the same coloring, right? So in that case, what happens? For example, let us say that I have this strip, and I color the first one with color A, second with B, third with C. Then I color the fourth with B, and the final one with A again. Now, if I reflect this, there is no difference. I get the same coloring, right, of the squares. And therefore, when I divide by 2, I am actually undercounting, right? So I need to take care of this. So I want to make sure that I don't overlook these kind of colorings. So what I do is that I just observe that the only type of colorings which which remains the same under the reflection are are precisely or rotation by 180, right? Rotation by 180 are precisely the colorings where some three colors are used in the first three boxes, and then the color of the second cell is used on the fourth, and the color of the first cell is used on the fifth. So any coloring like this, if I rotate, I will get the same coloring, right? Precisely the same. So therefore, such colorings I want to treat separately. So out of the total n raised to 5 colorings, right? This n cube colorings, because the first three cells I can choose any of the n colors, but then there is no choice because I just use the colors that I already have on the remaining cells. Okay? So out of this n raised to 5 minus n raised to 3 colorings, each of them under the rotation will give a different coloring, but they are equivalent. So therefore I can divide by 2. But on the other hand, I have this n cube colorings which are the same under the rotation also. So I have to add that. So this will be n raised to 5 plus n raised to 3 by 2. So we get this to be the number of inequivalent colorings, right? The distinct colorings where two colorings are same under rotation by 180 degree. Now, let us try to see how much more we can go in this direction, right? So the idea of Polya theory is to somehow generalize this. So what is the kind of thing that we can use to generalize something like this? So one thing that we observe, if you think about this, is this rotation that we are talking about, for example, is a kind of symmetry, or in fact it is a type of permutation of the elements of the set, right? So basically I'm permuting. I can think of this rotation as permuting the cells of this uh, of the set of squares, right? So or the squares, individual squares. For example, I can say that this rotation is basically like I'm permuting this square, right, going here, and this square going here. Similarly, this one going here and this one going here, and this square is mapped to itself. So such permutations, right, will give you the effect of rotation. And of course, the identity permutation will keep the same coloring. So if you want to think of this, you can think of this as basically these two permutations, identity and the permutation that maps 1 to 5 and 5 to 1, right? Then 2 to 4 and 4 to 2, and 3 to itself, right? The squares to itself as representing the rotation. And then you see that, okay, these two basically form a two-element group, and it is going to be a subgroup of the symmetric group of all the permutations of the squares, things like that. So before going further with this, let me just recall what is this group and all we are talking about. It's a very quick review because I expect all of you to know group theory. So what is a group? Group is basically a set, right? Let's say G together with a binary operation such that this binary operation, under the binary operation, the set is closed. That if I add elements of the set, I will get still another element of the set. So it is closed under this binary operation. Now, then we have some additional properties, right? The group properties which are, for example, associativity, right, of the addition, right? Then existence of identity, identity element. Then existence of inverse element. Right? So these are the properties that we want, for a group to have, right? So, so we have such structures which we call groups. Now, example of a group, for example, is the set of all integers under addition. Now, if groups have subgroups, what is a subgroup? Subgroup of a group is basically a subset of the set G, and such that X plus, right, is a group by itself. A group. So if this is true for some subset, then it's called a subgroup. Okay, so we follow the same binary operation, the same rules, and this subset together with the binary operation is a group by itself. Then it's a subgroup of the group. Then associated concept is what is that? Is that of coset, right? Cosets, with respect to a subgroup, I can say that G is an element of G and H is a subgroup. Then elements GH are the left cosets. And similarly, you can define right cosets. And cosets partition the group. Right? So this is something that you can take it as a homework and prove if you have not done it before. So the cosets basically form a partition of the group. Now, and with respect to which subgroup you are looking at, you will see that the cosets have the same cardinality, and then it follows that the order of the subgroup, so the number of elements in subgroup, divides the order of the group, and things like that. So these results are all very standard in the in any mention of group theory. Okay, so now these things that you should know. Then another related concept is the action of a group on a set. Okay, so group acting on sets. So let's say that X is a set, right? Let's say that n element set, right? Okay, X is an n element set, and G is a group. Okay. Now we say that the group G acts on the set X. G acts on the set X if for every element of the group, if for every element, let's say, of the group G, we can we can associate a permutation. Okay? We can associate a permutation, and we will overload the symbol by saying that pi is also a permutation. Okay? So we will use the same thing, permutation of X, right? So permutation of the elements of X, such that for every element X in X, and two elements, let's say pi and sigma in G, we have pi of sigma of X equal to pi sigma of X. Okay, so pi sigma is basically the the operation under the group, right? So it's a binary operation in the group. So pi sigma I get, and then pi sigma is an element of the group. So therefore it has a corresponding associated permutation, right? Every element is associated permutation. So pi sigma is now an element which is also representing some permutation, right? So pi of sigma of x is equal to pi sigma of x. So if this is true for every x and every pi and sigma, then we say that the group G acts on X. Okay. Now, if you think about this, maybe you should try to give an argument why. The action of the group G is the same as a homomorphism. Okay, so action of the group G on the set X is equivalent to saying that there is a homomorphism say homomorphism, let's say 5, which maps from G to the symmetric group Sx. Okay. So Sx is the set of all permutations of X. Okay, so this is the symmetric group Sx. Now, this is something that you can work out the details and make sure that you understand what is a group, what's a coset, what is action of a group on sets and things like that. So these things you should be clear. Okay. So once this is clear, we can proceed. Now, so let us try to look these things in a more general way. So let us start with a set X, which is a finite set. Okay. Now we consider a group G as a subgroup of Sx, which is the symmetric group. Now this is this group is basically a group of symmetries of X, right? Because permutations can basically, as a group, can represent symmetries, and that is precisely the reason we call the group of permutations as the symmetric group itself. Now we have this group of symmetries. We have this group of symmetries, and in fact, see, when we are talking about the definition, when we are uh, defining the groups acting on sets, we are saying that we are basically associating permutations with this. But now one can see that whichever group that you find, you start with, you can uh, associate permutations, then that permutations form a subgroup of a symmetric group, and then you can as well start with the symmetric group as your group that you are looking at. Now, suppose so you have this finite set X, you have a group G, and then consider a set of colors, okay, C, which could be an infinite set of colors. Okay, so C could be finite or infinite. And elements of C are called colors. And a coloring of the set X is basically a function from X to C. Right? So you're basically associating colors with elements. Right? So we have now a coloring of an arbitrary finite set X. Then we can we can of course ask several questions like what are the number of colorings. Then we can ask like if under the action of this symmetry a symmetric group G, can you say how many inequivalent colorings are there? So this is basically a generalization of what we were looking before. So let us look at an example. So X is the set of squares of a 2x2 chessboard or board labeled as let's say, okay, I think I have. Mhm. 1, 2, 3, 4. Okay, so maybe I will redraw this. So I have these 4 squares, 1, 2, 3, 4, right? Now let us say that C is this finite set R comma B comma Y. It's a set of colors, so red, blue, and yellow. Okay. The coloring of X is using the colors from C. Can be one of the examples is, for example, you give the first cell as R, second as blue, then the third as yellow, and the fourth as red, right? So RBYR, which means that F map from X to C is f of 1 is equal to R, f of 2 is equal to B, f of 3 is equal to Y, and f of 4 is equal to R, right? So we have a coloring of a finite set X. Right? Now, given this, we can ask some questions, and for that, let us define the following. So we define two colorings F and G, to be equivalent or G equivalent, and we denote it by F tilde G, right? So F tilde G says that F and G are equivalent. If we can find some permutation in G, because G is a symmetric group. So if we can find a permutation in G such that G of pi of x is equal to f of x for every x in x, right? So if I can do this, then we say that f and G are equivalent. So we can write, for example, G pi is equal to f, right? The composition of G and pi is basically the coloring, right? Now, so coloring F, right? So now prove that this relation that we defined, the equivalence relation, right? So G equivalent is an equivalence relation, right? I mean, so the reason we call this as when they are equivalent is because this happens to be an equivalence relation, but you need to prove this. So it's quite easy. Just prove that tilde is an equivalence relation. Continuing our example, so we have the set X, which is the set of all set of these 4 squares, right? And C is the colors R, B, and Y. Now the symmetry group G, right? So we said that G is basically is a subgroup of the symmetric group on all these elements on X, Sx. And since our Sx in this case is basically S of 1, 2, 3, 4, right? There are four elements at X. So we can look at any of the subgroups of this S4. So for example, maybe the symmetry group is precisely the identity permutation. The identity by itself forms a group, so therefore it's a subgroup of the symmetric group Sx, right? So G1, let me say, is the group with only one element, which is identity permutation. So what is identity permutation? This 1 goes to itself, 2 goes to itself, right? 3 goes to itself, and 4 goes to itself. So all the elements goes to itself. Then G2, right? So is basically the vertical reflections. So if you look at the vertical reflection, what happens if I take a vertical mirror and then reflect on this? Then you will see that under the reflection, 1 will be going to 2, right? So we have this labeling, right? What is that? 1, 2, 3, 4, right? 1 will be going to 2, and 3 will be going to 4. So this is represented by this permutation: 1 going to 2 and 3 going to 4. Of course, the identity is always equivalent, right? The coloring is equivalent to itself. So therefore, identity is always there. So therefore, we have G2 is consisting of these two permutations, 1, 2, 3, and 4, right? And 1, 2, 3, 4, right? So these two permutations form another subgroup with just two elements. Then we can look at the reflection on the main diagonal, right? So, I mean, I can put a mirror on the diagonal and then try to find the reflection. So 1, 2, 3, 4 again is there. Now, what happens under the reflection on the main diagonal? Of course, this cell will be preserved as it is, right? This cell will remain as it is, but this will go here and this will go here. So basically, this is represented by one going to itself, 4 going to itself, and 2 is going to 3 and 3 going to 2, right? So G3 is the reflection on the main diagonal. That is also a two element subgroup. Now you will see that as abstract groups, if you have studied group theory, you will see that abstract groups, G2 and G3, for example, right, are isomorphic. Okay? We have not defined isomorphism, but in any group theory course you will see. So they are isomorphic, but we will see that their actions are different, right? So as permutation groups, they are basically different objects. We will see this soon. Then we look at G4 as the group of rotations of X. So what is basically the rotations? Rotations are basically like, so this 1, 2, 3, 4 is there, right? I just rotate the entire figure, right, by 90 degrees. So these are the rotations. And what are the what are the elements of the permutation group which does this job, right? Of course, the identity is the rotation where we don't do anything, right? Then 1 going to 2, 2 going to 4, and 4 going to 3, and 3 going to 1. Okay. So 1 going to 2, 2 going to 4, 4 going to 3, and 3 going to 1. It's one rotation by 90 degrees. Right. Then if I have 2 rotations, then 1 will go to 4, right, after 2 rotations. And 2 will go to 3, right? And 3 will go to 2, and similarly 4 will go to 1, right? So I get this permutation. And similarly, if I rotate 3 times or rotate to the left, then I will get 1, 3, 4, 2. So 1 going to 3, 3 going to 4, 4 going to 2, and 2 going to 1. So these are the rotations, and these form a subgroup, which is called G4 in our case. Then we can talk about G5, which is the dihedral group of all rotations and reflections. Okay? So we already saw that the rotation has all these 4 elements. Then we have the reflections, right? Reflections on the main diagonal and the horizontal, vertical, etc. So these forms altogether 8 elements. So what are the elements? So the reflections 1 going to 2, 3 going to 4, right? So 1 going to 2 and 3 going to 4. So that is the reflection, vertical reflection. Then 1 going to 3 and 2 going to 4, which is the horizontal reflection. Then 1 and 4 remains, 2 and 3 are interchanged, which is the reflection on the main diagonal. And then 2 and 3 are remaining itself, and 1 is going to 4, which is a reflection on this this diagonal, right? Diagonal including 2 and 3. So this is the dihedral group, which consists of all rotations and reflections. Then finally, we can also look at the symmetry group of all permutations of X, G6. Okay, so Sx is S4 itself. Now, so if you look at all possible permutations, then we see that actually it loses the connection with the geometric representation of X as a as this 2 by 2 square, right? Because when we allow all possible permutations, right, then and they are all considered identical, then there is precisely nothing to differentiate, like whether there is this figure where is this figure or not, right? Whatever the shape of the figure, it's instead of 1 2 3 4 as a 2 by 2 square, you can have it 1 2 3 4 as a as a line, not line. I mean, as a sequence of four these things. Or put in another fashion, all of these are immaterial. What is the shape? It does not matter. So you will see that the when you take the full symmetric group, then the shape or geometric representation does not matter. So that we lose the meaning. But of course, it's a valid permutation group. Then under all these six groups, we can talk about the inequivalent colorings of X, where we specify our set of colors. Let's say we are saying that we always use two red colors, right? Like two squares will be colored with red always, and one will be colored with blue, and one will be colored with yellow, for example, right? So if you specify the number of times each color appears, then we can talk about the action of the group. So in case of the in the group is G1, right? So of course there are 12 colorings, right? There are 12 colorings when we are using two colors for red, right? So there are four squares. Two of them are always going to be colored red, right? So it doesn't matter, the first red or second red. There is no difference. So therefore, we need to just look at the all possible colorings under so basically we have 4 factorial possibilities, but two of them are the same by 2 factorial. So you have the multi-set. This is the first thing that we learned in our course. So therefore we have 12 colorings, and all are inequivalent under the trivial group, right? Because the identity group, right? I mean, we are not allowing any changes to be made. So once you fix the 12 different colorings, they are all going to be inequivalent. Right? They are all different. So then G2 is the group where we allow the vertical reflection, right? So under vertical reflection, we can see that there are 6 inequivalent colorings. So why is this? For example, under the vertical reflection, you have RRBY, right? And it is basically like if you put a reflection, and then you have RRYB also, right? So RRBY and RRYB belong to this particular one class. Then similarly, you will see that under vertical reflection, this one, for example, right, is equivalent to RR, here, and B and Y are interchanged, right? Similarly, in each of these, you will see, you can all find, one another coloring to which this is actually identical under the reflection, right? So under reflection, you take the reflection of this, whatever you get, they are both equivalent. So you get 6 inequivalent colorings because these two are equivalent, these two are equivalent, these two are equivalent, these two are equivalent, etc. Right? So under the action of G2, you have exactly 6 colorings. Now under G3, okay, so reflection on the main diagonal, you will see it is slightly different. This is why I said G2 and G3 may be isomorphic as abstract subgroups, but under as symmetric groups, as permutation groups, they are different. For example, the action of G3 here is slightly different, right? So you will see that if you look at these colorings, right? So each of these colorings, under the reflection on the main diagonal, right? You will see another coloring, right? So you will see that, for example, B here and R here. This is a different coloring, and they are in equivalent. Again, Y and R are swapped. R and Y are swapped here, right? And similarly, R and B are swapped here. Again, Y and B are swapped here. So they are all having two elements in the class. So you will see that. But on the other hand, this one, right, B Y R R, Under reflection, this does not give anything else, right? So it remains the same. So therefore, there is only one element in its class. Similarly, if you look at YB and RR again, right? So there is only one element in this class. So these are different, right? Under the reflection with respect to main diagonal. So therefore, instead of the 6 we had here, right? 6 inequivalent colorings, we have 7 inequivalent colorings here, right? 1, 2, 3, 4, 5, and 6, 7. So G2 and G3 are isomorphic as subtract groups, but as permutation groups have different structure. And if you think about it, you will see that the difference comes from the difference in the cycle structure. Cycle lengths of elements are different. For example, here 1, 2, 3, 4, right? 1, 2 is a cycle, 3, 4 is a cycle. There are two cycles of length 2. On the other hand, under the reflection on the diagonal, you have two 1 cycles and 1 2 cycle. So, this is precisely what makes them different, right? So they are the difference in their action is precisely because of the difference in the cycle structure. So we will see more about this when we go. In fact, we are going to make use of precisely this observation, and that is the essential part of our Polya theory. And then we have G4, and G4 is the dihedral group, right? Dihedral group. G4 is the group of rotations of X, right? So all possible rotations, and there are 3 classes with 4 elements. Okay, so sizes of each class equals the order of the group. So why is that? For example, what is the order of the group? It is 4, right? There are 4 rotations of this identity, and then the 3 other rotations. And why they are why they're precisely 4? Because you will see that under rotation, and no coloring has symmetry with respect to this rotation, right? So you take any coloring that we have, right? If after rotation, if it remains, so we have this 12 colorings that we started with, right? We did not draw them, but think of this. You can take an example and draw them. So take any of the 12 different colorings. Not any. Take all the 12 different colorings and see that if you apply rotation, they are always going to be inequivalent. So therefore, there are 3 rotated elements other than the identity. So therefore, every class has exactly 4 elements. All the permutations, the identity as well as the other 3 permutations. They will all give different colorings, and each of them are equivalent under rotations. So therefore, you will see that if you rotate this, you will get 3 more different colorings. If you rotate this, you will get another 3. If you rotate this, you will get another 3. So therefore, all the 12 colorings appear here. So G4 is the group. Now G5 is the dihedral group. So under the dihedral group, we have only 2 elements. Okay. So the first class has 8 elements and second class has 4 elements. So you will see they are different because under the reflection, these R and R, right? They will not change, and therefore you have less number of elements in this class, and you can verify that this has 8 elements, right? So if you do all possible rotations and reflections, you will see that this will lead to 8 different objects that we are going to. Now, another observation that we can make is that the size of a class is the index in G of the subgroup fixing some fixed coloring in that class. Okay. So think of this and try to see why. Okay. So size of class is the the subgroup fixing some fixed coloring in that class for for any uh, action of a group. This is a property that you can observe. Then you have finally G6, which is the set of all permutation. There is only one class, because we are saying that no matter what permutation we take, we get the, we are saying that they are all equivalent, right? So therefore, by permutation, you can always get a coloring from one to other. If the number of colors, number of times each color appears is the same, right? So since we started with saying that, now we have exactly two red squares and one blue and one yellow square. The number of cells in which red appears is always 2, right? And number of times blue appears is always 1. Number of times yellow appears is always 1, right? So therefore, we see that when you take permutations, right? Permutation cannot change the number of times a color appears, right? We are just saying that, okay, this cell is mapped to this cell, that cell goes to this cell, etc. But the colorings remains same, for example, right? So therefore, the number of times each color appears is always different. So that is it. So we have these 6 groups, and each group acts on the set of the set X, and then this action will also give different colorings, and then under this action of the permutations, we can say that they are basically symmetries that we are looking at of the object, and these symmetries will tell you how many different colorings we can have under the how many different inequivalent colorings are there under this action of symmetries. Now, so I forgot to mention what is index of a subgroup. So index of a subgroup is the number of cosets, left cosets, or equivalently number of right cosets. So when I said that the size of a class is the index in G, what I said is that if you look at the subgroup of a group that we are looking at, so take a subgroup and then look at what is the number of cosets this subgroup has in G, right? So that is called the index. So now it should make more sense, and then see why this is precisely the number of elements that appears in that class. Okay? So this should give you a better. Uh, Now, this is why I said that we should also look at cosets. Now consider the same set that we are looking at, where we consider the group which is the dihedral group, right, of all rotations and reflections. Now, under this, let us talk about by denoting by t of I comma j comma k. There is a comma missing here, I think. The number of inequivalent colorings using the colors R, B, and Y of X, using the color red I times, right? Color blue J times, and color yellow K times. Okay. So we have the set X. You have the dihedral group acting on this, and we are looking at the number of inequivalent colorings under the action of the dihedral group, where the red color appears I times precisely, blue color appears j times precisely, and yellow color appears k times. Right? So earlier we were looking at two red, one blue, and one yellow. Now we can say that, okay, instead of this, let us say that we have I times red, j times blue, and k times yellow. Now, of course, if you are having x has exactly four elements, we should be clear that, like, I plus j plus k must be 4, right? Because we are coloring all the cells, and it can only change within this restriction. Then now we want to collect the information basically that counts, right? T of I j k for different values into a generating function, right? So this is something that we are already familiar with. So let us write fg of r comma b comma y as this summation over all I plus j plus k is equal to 4, because we have only 4 elements, and we have to color them all. So therefore 4 times the colors altogether can appear exactly 4 times. So I plus j plus k is equal to 4. T of I j k, right, which is the coefficient of r raised to I, b raised to j, and y raised to k. So r, b, y can be considered as variables, right, of the generating function. So instead of one variable, now we have several variables, right? So 3 variables here. So, and if you look at the coefficient of r raised to I, b raised to j, and y raised to k, it should precisely tell you, right, how many colorings are there, right? Inequivalent colorings are there under the action of g, that is yfg. Like I appears, r appears I times, b appears j times, and y appears k times, right? And that exactly that number is what we are looking at here, right? Which is t of I comma j comma k. So that is what we have. So we are putting it into the form of a generating function. This is how we define generating functions anyway. So our generating function fg of rby is this one. Now what is value? Okay, so we can verify that it's actually equal to. Okay, so you work out the details. Okay, looking at each color appears this, and you see that how many are there, and then apply the dihedral group and see how many equivalent colorings are there. Okay, so you will see that this is actually going to be equal to r raised to 4 plus b raised to 4 plus y raised to 4, right? Because there is only one coloring where all the cells are colored with the red, right? Red appears 4 times, means that I have one coloring and that's it. I mean, whatever else you are going to do, it's going to be the same, right? If you are using only red color. So similarly, b raised to 4, y raised to 4 is very clear. Similarly, r raised to b, r raised to 3b, right? So all three colored red, and then one is blue. Of course, you have different colorings, but then under the action of dihedral group, you will see that they are all the same, because by rotation you can get this, right? Similarly, rb raised to 3, r raised to 3y, and ry raised to 3, b raised to 3y, by raised to 3, right? So if I'm using only two colors, one of them 3 times, then you have this. But on the other hand, if you are using colors 2 times, right? So r, for example, is appearing 2 times, r square, and b is appearing 2 times. Then you will see that you will see two different coloring, right? So even under the action of dihedral group, you will see that there are two different colorings are possible. And similarly for r square, y square, b square, y square, etc. And then, as we checked before, r square by, right? Right, r is appearing twice, b is appearing once, and y appearing once. This is precisely what we calculated in the previous example, right? Where we are looking at this, we say that there are two in this class, right? G5 has exactly two, right? These are the two representatives here. So you will get 2, and for all the other symmetric cases, right? R b square y, R b y square. So check this. I mean, it's quite easy, and make sure that this is precisely the generating function that we are looking at. Now, it's easy to observe and also cy that fg of rby, right, is symmetric in all its variables, right, r, b, and y. Since the names of colors does not make any difference. I mean, I can call red as blue and blue as red, right? Just renaming. So therefore, it should be symmetric. Okay, so we have this, and now let us look at some things from this. So if you look at fg, right, fg, and look at fg of r, b, and y, I substitute with the value 1, right? So r becomes 1, b becomes 1, and y becomes 1. And what happens to this right hand side, right? So you'll get 1 plus 1 plus 1 here, right? Then you have again 1 plus 1 plus 1 plus 1 plus 1 plus 1, right? 2 into 1 plus 1 plus 1, 2 into 1 plus 1 plus 1, right? So altogether, what you will get? Okay. So see what you will get there, and you should get the total number of inequivalent coloring, right? I mean, without the uh, without the restriction on a specific number of times each color appears, you will see that if you are using, the coloring using these colors on the four vertices, four squares, you will see that this is precisely the number of coloring possible, which is 3 plus 1, 2, 3, 4, 5, 6, right? 3 plus 6 plus 6 plus 6, right? Right. So 6 plus 6, 12 plus 1, 2, 3, 4, 5, 6 plus 6 plus another 3, right? So this will be your total number of inequivalent colors. So you can verify that. Now, to generalize, let us use an n element color set, right, instead of the 3 element set. Let us say that we are using R1, R2, R3, etc., Rn, right, to color the set X. So we use more colors, then what can we see? Right? So the names does not matter, only the multiplication of the colors matter, right? Right, multiplicities of the colors. How many times a color appears can make the difference. And again, the order of this color, in which this, multiplicity occur also does not matter. So what are the possible cases? So one possible case is that all four colors are the same, right? We have R1 is appearing in all vertices, R2 is appearing all, etc. Or one color appears thrice and another one appears once, right? This is another possibility. We have only four colors to color, and four squares to color, right? Then two squares are given, the same color, and another two colors are given the same color, right? Using two different colors. Then one color appears twice, and two colors are appearing only once. Then four colors are all four distinct colors, right? So these are the possible cases, and there is nothing else one can easily verify. Now these five cases correspond to the five partitions of four. This is something that you should observe, which may be not very easy, but if you think about this, it comes true. Okay, that is basically what are the partitions of four? We have 4 by itself. Then you have 3 plus 1, right? 2 plus 2. These are the integer partitions we have looked before. Then you have 2 plus 1 plus 1 and 1 plus 1 plus 1 plus 1, right? So this basically corresponds to partitions of integers, right? So if you have the total number of boxes to color is 4, then all it matters, right? If you have enough colors to color from, all it matters is that how many times a color appears, and basically the multiplicities of the colors. And since the order does not matter, you will get this as exactly the partitions of 4, not combinations, right? So with respect to the first one, you will see that all colors are same, A, they are all identical. Then for 3 plus 1, you have A and B, right? Then you have AA, BB, or A and A in the diagonal, B and B in the diagonal, right? They are different. Then you have AA in the diagonal, B and C are different, right? So which is 2 plus 1 plus 1. And similarly, you have AA here and B, C, again 2 plus 1 plus 1. Then you have all four different, so A, B, C, D, A, C, B, D, or A, C, D, B, right? So once you have this, it is easy to find out the generating function. So what is fg of R1, R2, etc., Rn? It is summation over all Ri raised to 4 for different colors. You can have this all to be the same. Then if I and j are different, summation overall I not equal to j, r raised to ri raised to 3 and rj, right, for different I and j, right? We need use two colors. One appears 3 times, one appears only once. Then we use two colors, I and j are different, but I less than j, where because order does not matter, right? So ri appears twice and rj appears twice, right? But there are two possibilities here, right? One is mm, one is I less than j, and then the other one I greater than j. Then again, one color Ra appears twice, and Rj and Rk appears exactly once. So I not equal to j, of course. I not equal to k also, and j is less than k. I know Rj and Rk are different. But again, j is less than k and j is greater than k. Two different cases. So there are two into this. Similarly, you have 3 summation over I less than j less than k less than L, right? This inequality holds, and there are 3 such possible arrangements. And you will see that this is precisely the generating function that we have, right? And as we saw in the previous case, if you substitute for all the variables to be 1, it will give you the total number of inequivalent colorings, where I use exactly n colors. Okay, so you verify this, and you can find out the numbers if you want. And what is the number FG1111? That is precisely, so in the first case you have n, right? So n different colors we are using, and each one you will get one. And then you have Ri cube Rj, right? I not equal to j. So there is n into n minus 1 cases, right? Good. First color I have n choices, second color I have n minus 1 choices. Similarly, for the third, I have 2 times n choose 2. Then you have 2 times n into n minus 1 choose 2, right? And for the finally, you have 3 times n choose 4. So you will see all these things, verify all these things. As a homework, you can think of this and try to verify these things. And what is this actually? I know this is the more interesting part. This FG1111 is actually equal to 1 by 8 n raised to 4 plus 2 n cube plus 3 n square plus 2 n. Okay. So if you simplify this, right, FG1111, you will see that you can write this as this formula. And 1 by 8 comes nicely. You can take 1 by 8 outside once you do this simplification. Okay. And then what we observe from here is that the denominator 8 is actually equal to the order of the dihedral group, right? So dihedral group G5 has exactly 8 elements, and 8 happens to be the denominator. And it's not a coincidence, we will see later. Now, the coefficient of n raised to I, right? N raised to 4, for example, right, is the number of permutations in G5 with I cycles. So how many permutations are there with 4 uh, cycles? There is precisely 1, right? So therefore I get coefficient of n raised to 4 to be 1. Now similarly, you will have 2 permutations, in G5, where where you have three cycles are. Let's look at the permutations actually, right? So what are the permutations in G5, right? So G5, has this identity. Then you have 1 2 4 3, right? 1 4 2 3 1 3 4 2, and then you have uh, 1 2 3 4 1 3 2 4 1 4 and 2 3 and 2 3 and 1 4, right? So these are the dihedral groups. And now what we are saying is that so how many like how many cycles are there with exactly how many pyramids are with exactly three cycles? So we want to count that, right? So we will see that, and this one, for where is that marker? Yeah, so I have this one has three cycles. This one has three cycles, right? Anything else has having three cycles? Nothing, right? So we have coefficient of this is going to be 2, right? Coefficient is 2 here. Similarly, you will see that permutation with exactly two cycles, so will be coefficient will be 3. There will be three of them, and one cycle there is two of them, right? And that is it. So this is an observation that we can make. Okay, and then yeah, so this is one example that I had already written here. Uh, Now we want to show that this is actually the case for all such situations, right? So you will have the coefficients of these terms are going to be precisely the number of uh, times uh, number of times you can find a permutation or number of permutations in the group that we are looking at, having exactly three cycles, exactly four cycles, exactly two cycles, and exactly one cycle, right? So this can be generalized. That is what it says. So here we have the Burnside's lemma. Burnside's lemma says the following. So let Y be a finite set, right? And G be a subgroup of Sy. Now, for some permutation in G, let's say pi, the set fix of pi is the set of all elements Y such that pi of Y is Y. That the elements which are unchanged under the action of pi. Right. The permutations may not change some elements. Right. So if I take for example the identity permutation, it does not change any element, right? Similarly, we have 1 going to itself, 2 going to itself, 3 and 4 are interchange, right, in the dihedral group that we looked at. That is another permutation where 1 and 2 are fixed, right? So similarly, given you know given a permutation, we can see the set of all elements that are fixed by this permutation. So that is the fix of pi. Now the cardinality of this set, right? So that is cardinality of x of pi is the number of cycles of length 1 in the permutation pi, right? That is clear because basically the cycle representation of the permutation tells you which are the elements that are mapped to itself. These are the unit cycles, right? When we put a single element in the bracket in the cycle notation, that tells you that these elements are the fixed elements, right? So the fix of pi is the number of cycles of length 1 in the permutation pi. Suppose we denote by y mod g as the set of orbits of G. Okay, so what is the orbit of a group? Basically, when the group acts on a set, it basically moves the elements. So then we can look at the look at the elements which come under a class, right? So we are saying about the classes. So some elements are basically moved to other elements, right? Mapped to other elements, and then this forms a subset. So this is basically the orbit. Then the cardinality of y mod g is actually equal to 1 by cardinality of g, summation over all the permutations in G, the cardinality of the fix of y, right? Here is the number of orbits of G is equal to the average number of elements of y fixed by the elements of G. This is what Burnside's lemma says. Okay, so we will see a proof for this in the next class.